Ladies and gentlemen, welcome to my presentation, Dry and Wet Granulated Blast Furnace Slags Comparison of their cementitious properties. I will inform you on the motivation and targets of the projects. I inform you on the dry granulation tests in a technical facility and in a demonstration plant. I will inform you on the technical properties of the DSG pellets made in the demonstration plant at voestalpine in Linz. I will inform you on the cementitious properties and our glass analysis, and I will give, of course, some conclusions. Each ton of blast furnace slag and steel slag contains 1.6 to 1.8 gigajoule per ton terminal heat. However, as well the water granulation for GBS as the slag pit cooling wastes the heat. Utilization would be a contribution to reduce the environmental impact of the steel production. Dry granulation is a precondition for heat recovery in a heat exchanger, and the high glass content of the granulated blast furnace is a precondition for its use as a latent hydraulic cement constituent or concrete addition. Thus, we had for our projects three main targets. Dry cooling, to be able to create heat recovery, to be used for hot blast stoves, for steam or electrical power generation. Fast cooling, to achieve glassy structure. And a stable process, which is able to handle high slag flows up to 12 tons per minute at the end. In 2011, we started a first project together with Siemens. It was a technical facility plant which was able to handle 300 kilogram batches. Starting in 2013, we had two projects together with Primetals, voestalpine and the Montan University in Leoben, in a demonstration plant which was able to handle slag flows up to 1 ton per minute. Today I will inform you on this project. All projects were based on the rotating cup principle, which was developed by Davy in the 1990s. There was already a demonstration plant at British Steel in Redcar. The same principle was used today. In the middle you see the rotating cup. You have a covering to be able to use the hot air in a heat exchanger. And at the basis, you see the fluid bed with a fresh dry slag granulated particles, pellets. But in the beginning of the process of the test, you have to start with wet granulated blast furnace slag to be able to have some materials inside the installation. After the test, we got mixed samples consisting of classical wet granulated GBS, new produced, dry produced DSG pellets, some agglomerates of the pellets, and some crystalline slag. The DSG pellets accounts to about 1/3, in that case 38% of the whole sample, and the main part of the DSG pellets was between 1 and 3 millimeters. The glass contents were always very high, about 100 volume%. The chemical composition of as well the industrial GBS 13B, which was our reference, as all DSG pellets from the 3 campaigns was very similar. In particular, the chemical composition of the different fractions which we separated from the pellets from the same campaign were very similar. All in all, the slags had a low basicity, so the reactivity of all slags was in general lower compared to other slags which we have in Europe. Looking to the grading curves, the DSG pellets are coarser compared to most GBS, and also compared to the wet granulated GBS 13B from Linz. That is very important for the later discussion. The particles are spherical and very dense, as you can see here in SEM picture and 3D CT analysis picture. To evaluate the cementitious properties, we have normally the same procedure. We grind the slag to our standard fineness, which is about 4,200 Blaine. We mix the ground slag, 75% of the slag with 25% of our standard clinker with the same standard fineness and some sulfates. We use this high amount of slag because then we can see the dominant influence of the slag and slag modification. After mixing the cement, we measure as well the strength development of mortars as the heat of hydration of cement lime according to the European standards. The result of our grinding, you can see here the finest parameters, very similar, so all materials had a very similar fineness. First, we look to the compressive strength. The early strength is very low due to the high slag content. Of high interest is that you can see that all strengths from cements made with these G pellets are significantly lower compared to the slag cement with industrial GBS. Between the fractions of the DSG pellets of the same campaign, there is no difference. Looking to the heat of hydration, after 12 hours, you see the typical clinker peak. For the wet granulated slag, you see after 54 hours, the typical second peak for the GBS. The peak in that case is very low due to the low basicity and low reactivity of the slag. But for the DSG pellets, the second peak is still lower and very similar. The glass analysis, which we use to explain the differences of the properties, were already explained, the principle was explained during the last slag valorization symposium and also in 2 publications in the Journal of Sustainable Metallurgy and in the Journal of Non-Crystalline Solids. Therefore, I want not to explain too much, but we are able to measure as well the glass transformation temperature Tg, which is measured under standard laboratory frame conditions, cooling rate, heating rate 10 Kelvin per minute. But we are also able to calculate the so-called fictive temperature, that is a glass transformation temperature under real conditions, which you cannot measure directly. If you have the so-called fictive temperature, so the real freezing temperature, and if you know the viscosity at this temperature, you are able to calculate the cooling rate Q. The cooling rate is normally in the range between 1,000 and 10,000 Kelvin per second, very fast. The results of the glass analysis, which were done by our colleagues from the Technical University of Clausthal, you can see here. It is important to say that we measured unground particles of different sizes. We used small, medium, and large particles, and therefore we have to differentiate between the different particles and to compare only particles of the same fraction. First, we look to Tg, the glass transformation temperature under standard conditions, and you can see that there are nearly no differences because the chemistry of all the slags was very similar. The case is another one for the fictive temperature. First, we look to the small particles, and you can see that the fictive temperature for the DSG pellets of the same size is lower. The same effect you can see for the larger particles. For fine particles, as compared to L, TF is higher. As well for the wet granulated slag, but also for the dry slag granulated pellets. The fictive temperature correlates with the cooling rate, as I explained. Looking to the same particle size, the cooling rate for the wet granulated slag is much more higher compared to the dry granulated slags, despite the fact that the temperature, the viscosity is very similar. And also the same effect for the large particles. Comparing bigger particles and smaller particles in general, you see that also for the red granulated blast furnace slag, larger particles are cooled down slowly compared, or more slowly compared to smaller particles. The same effect for the dry granulated slags. Thus, we came to the following conclusions. The dry granulation based on the rotating cup principle achieves high glass contents, very high glass contents. Thus, the basis for the latent hydraulic reactivity and the cementitious applications is secured. However, the reactivity of the DSG pellets is given but lower compared to wet granulated GBS of a comparable chemistry, glass content, fineness, etc. We could show that for very different slag chemistries, as well in a technical facility as in a demonstration plant. In a technical facility, we had different chemistries and much more different compared to the chemistry in the demonstration plant, but the same effect. And the lower reactivity results from the lower cooling rate corresponding with the lower fictive temperature TF. And the lower cooling rates results as well from the general worse heat removal by air instead of water and from coarser particle sizes compared to GBS due to the particle forming process in the dry granulation process. There are still some questions to be answered. Verification with another slag chemistry, for example, with a higher basicity, which means other viscosity, other TG, etc. We have to look to slag handling in a pilot plant with a higher slag flow. And of course, at the end, the heat recovery has not yet been tested. If you want to read more in more details, you'll find it in Cement International, which is published soon. Also the informations on the tests made in the technical facility and not only in the demonstration plans are described here. At the end, thank you for your attention.